Hello everyone, welcome to my presentation. First of all, let me thank you all for being here today. It is my honor to have the opportunity to give a plenary presentation in front of such a distinguished audience. I would also like to thank IASS for inviting me here today. Let me introduce myself. I'm Jeff Lee, one of the 4 recipients of the 19th Hangai Prize. I am a postdoc researcher from the Center for Innovative Structures and Materials of RMIT University, Melbourne, Australia, under the supervision of Professor Mike Xie. In today's presentation, I will show you our new design strategy to create elegant and well-defined architecture forms using curved rulings. The title of my presentation is From Ruled Surfaces to Elastica-Ruled Surfaces, New Possibilities for Creating Architecture Forms. Let me start by giving you the introduction of ruled surfaces. In geometry, ruled surfaces are those that can be generated by utilizing the continuous motion of a straight line, moving along one space curve or 2 individual space curves. The straight line is called the ruling, and space curve is known as the directrix of the surface. The combination of ruling and directrix can be used to manipulate the shape of a curved surface. As shown on the screen, the concept of ruled surfaces can be used to create many beautiful and striking 3D shapes. That is to say, these configurations can all be described by a bunch of straight lines. Ruled surfaces are widely used for architecture forms, and the adoption of ruled surfaces have led to many innovative and iconic architecture forms. They are popular because elegant 3D shapes can be conveniently generated. For example, hyperbolic towers and spiral structures, as shown on the screen, can all be designed using the movement of straight rulings. Moreover, allowing the directrices to be movable can generate attractive connected architecture designs, such as the wave sculpture designed by Santiago Calatrava. Although ruled surfaces can create many elegant architecture forms, we believe that there is a huge potential to create a rich variety of new architecture forms by introducing curved rulings into ruled surfaces. To this end, we are making a fundamental change to existing ruled surfaces by replacing the straight lines with curved rulings. Here, we introduce the elastica curves, that is the large elastic bending deformations of a straight slender beam, which can also be understood as the minimum bending energy configurations. Analytical solutions for pin-to-pin elastica with uniform bending stiffness have been developed previously from the curvature equation using elliptic functions. To summarize, there are 4 elastica curve design parameters for each bent state, including the arc length L, support distance B, curve height H, and the initial tangent angle theta. Specifying any 2 curve design parameters, we can then obtain the shape of an elastica curve using xy coordinates. I would like to highlight that the elastica curves are purely geometric relations, so the same bent shape can be seen in any elastic material using equivalent structure systems. There are 3 key advantages of choosing elastica curves. Firstly, elastica curves can be parametrically controlled. Again, we can simply specify any 2 curve design parameters to design a unique elastica curve. For example, the elastica curves shown on the screen were obtained using a fixed arc length L with different support distances B. Secondly, elastica curves can be accurately designed. This is shown more clearly in the comparison between the design and manufactured elastica, where they have demonstrated a good agreement. Finally, elastica curves include a rich variety of natural bending configurations. In contrast to circular segments with uniform curvature, as shown on the right-hand side of the screen, each intermediate elastica curve on the left-hand side of the screen corresponds to a non-uniform curvature. We believe that the shape richness of such natural bending deformations is valuable. and something that we can utilize in the design of architecture forms. A new type of ruled surface composed of elastica-curved rulings is proposed, and we call that the elastica-ruled surface. First, we need a line ruled surface, and a straight line defines the support distance B of an elastica curve. Specifying one additional design parameter, L, H, or theta, gives an unique elastica curve. The beta parameter is then introduced to control the rotation of the elastica curve around the straight ruling. Creating the elastica curve on all straight rulings generates complete curved rulings, and sweeping all curved rulings gives a continuous elastica-ruled surface. Using this transformation method, we can conveniently, parametrically, and accurately create a rich variety of elegant 3D surfaces. I would like to highlight that a straight line is an undeformed state of the elastica, so the line ruled surface can be understood as an extreme elastica-ruled surface. In the following slides, I will show you more interesting transformation results. I will also show you the 5 categories of the elastica-ruled surfaces that we classify based on their shape features. Category 1 elastica-ruled surfaces are those start with planar line ruled surfaces. Interestingly, transforming a planar line ruled surface gives an out-of-plane pop-up elastica-ruled surface. In Category 2, if the line ruled surface is tubular or closed strip, this transformation may completely change the shape of the tube or strip. Category 3 starts with open line ruled surfaces, meaning the directrices are not closed curves. It can be seen that the generated elastica-ruled surface is also an open surface. In Category 4, if the line ruled surface is generated by a set of intersecting non-parallel rulings, the generated elastica-ruled surface may contain regions with intersected curved rulings. Last, in Category 5, if the line ruled surface is the assembly of 2 or more line ruled surfaces subjected to common geometry constraints, each line ruled surface can be transformed into an elastica-ruled surface locally and preserve the geometry connection. Elastica curves are obtained from the fundamental theory of elastic bending mechanics, so elastica-ruled surfaces composed of elastica rulings can be adopted for practical applications that consider elastic bending behavior. For example, if we utilize elastica-ruled surfaces in the design of bending active structures, we can accurately capture the curve shape of the full system and avoid the need for numerical form finding processes. 3D elastica-ruled surfaces can be rationalized using a series of non-interacting bending active elements that correspond to the elastica curved rulings. Moreover, elastica-ruled surfaces offer a wide range of hot blade cuttable geometries, which can be realized using numerous robotic hot wire cutting techniques. Kinetic architecture designs create dynamic structures with movable parts to enhance their aesthetic qualities in response to environmental changes. Elastic kinetic approach is one strategy that can trigger complex elastic deformations without using mechanically complex systems. By combining the elastic kinetic approach with elastica-ruled surfaces, we propose a novel type of dynamic forms, termed kinetic elastica-ruled surfaces, that may be achieved by continuously changing the bent states of curved rulings. As shown in these videos, interesting wave effects can be simply controlled by shifting or rotating the dynamic directrices, and we are currently working on the physical prototypes of these kinetic architecture designs. Finally, I would like to highlight that the elastica curves used in the previous examples are in the first mode, meaning they have only a single peak between their end supports. Interestingly, higher-order elastica curves can be obtained by assembling multiple identical first-mode elastica curves. That is to say, the shape of each first-mode elastica curve can be obtained from the same elastica curve design parameters mentioned earlier, including L, B, H, and theta. As shown on the screen, higher-order elastica curves can generate a corrugation effect. Adopting higher-order elastica curves in the generation of elastica-ruled surfaces gives higher-order elastica-ruled surfaces and offers a wide range of new design possibilities. Higher-order elastica-ruled surfaces can also be used to generate many interesting architecture forms. The four beautiful examples shown on the screen were designed using second, third, fourth, and seventh mode elastica curves. It can be seen that increasing the order number can amplify the corrugation effect. To conclude, we have proposed a new type of ruled surface that uses elastica curves as curved rulings to create elegant and well-defined architecture forms. Using the proposed ruled surface transformation process, we can conveniently obtain more varieties of 3D surfaces than those composed of straight rulings. Elastica-ruled surfaces composed of elastica rulings have high suitability for practical applications that consider elastic bending behavior. Adopting higher-order elastica curves in the generation of elastica-ruled surfaces further enhances the design diversity of elastica-ruled surfaces. This brings me to the end of my presentation. Thank you for listening. I will welcome any comments or questions from you. You may contact me through my email or my personal website using the links as shown on the screen. I look forward to having further discussions with you. Thank you.